Wait, I need Elijah. Can you get me one of my Red Bulls in the fridge? What's up, y'all? What's up? Good morning or afternoon. It's 1 o'clock already. 1 o'clock already. All right, let's get to work. All right. First, thank you, sir. I appreciate you, son. Go ahead and close that door for me if you don't mind, sir. Thank you very much. Love you. It's my man, my little man. What the hell? I don't like that. There you go. I don't like blue. There you go. There you go. Justin is like, all right, what's up, y'all? What's up? Good morning. Good morning. It's afternoon over here in Tampa, but what's up, y'all? How's everybody doing? Hope everybody's having a blessed day. A blessed day. We are working. Oh, shit. We got a result. Finally, boy. All right, good job, Jordan. All right, let me listen to this real quick. What's everybody doing? How's everybody's weekend going so far?
So I was looking at the price difference between our general VIP ticket and we're charging $200 for VIP and I'm trying to value the ticket, right? And I think to be honest, as it currently stands, I'm not sure VIP seating and early access is worth 4 times the general admission price. So I was thinking, since the people get in early, how about we set it up to where they can have like a meet and greet or mix and mingle with the educators since they get to come in early, right? So almost like not necessarily like a brunch or breakfast, but being able to chop it up with the educators and shit before we let everybody else in. What are your thoughts on that?
All righty. Hey, that's what's up. Good, I graduated in 2 weeks. Excited, a little lost, but ready. Let's go, Cash. Cash, are you in the mentorship? You won't be lost, bro. If you lock in with us, you will not be lost. All right, guys. So it looks like, man, we were having an issue with our ads here, but it looks like Jordan came in and fixed it. We already have one lead for this barbershop, and that lead cost, not a lead, but we already got one customer, so an appointment booking, so $3.40 for that booking. Can't complain about that. Cannot complain about that. Let's see how 6FB ads are going. All right. Let's see. Yesterday's sales. Nothing. No sales yesterday. What in the hell? But 10 for the week. Yo no sé mañana. Rose is looking atrocious. All right, let's look at Tomb 45 ads. How are those doing? Those are a little rough as well. What's going on, y'all? What's going on? All right, we're not gonna count those. We're gonna count these. We ain't counting none of those. All right, that's what we're counting. Let's see. Oh yeah, we good. So these ads are doing 4x ROAS. I ain't mad at that. That's doing good. They could improve, and they will over a little bit of time. Alrighty, let me get in the chat with my guys. Guys, I'm just going live all day, pretty much clipping if there's anything worth clipping. Let's see what's on YouTube. What's the news for today? Check the news. Bro, it's crazy how this is only 10% contained. The wildfire, 10% contained. They evacuated the Palisades again. Freaking insane. Like, it's bigger than New York City. The size of San Francisco has all burned down. To give you a comparison. Look at this. This is what I was talking about the other day. Tampa's flooding. That was the worst one in a century. And now we're seeing what's happening. And people were talking about Florida, not living in Florida because of hurricanes. I would rather deal with hurricanes than deal with this, man. This is crazy. These wildfires. I do want to listen to this, though.
But I did want to talk about the future. Mm-hmm. We talked about what y'all did right. We should talk about some incredible stories happening regarding, I was told that the county is out there still pumping out water from neighborhoods. And even though they can't pump it directly from the storm pumps, y'all are taking it out of neighborhoods and putting it in water trucks and hauling off the water. Mm-hmm. I think that's amazing, and we can dig into that. But I did want to talk about some lessons learned and some unexpected things that happened during these storms from an operational standpoint, but also from a public work standpoint, right? Do we need more drains? Do we need more generators for pumps? Like, how do we soften the effects of these storms that are a natural part of living in Florida and are certainly not going away?
Mm-hmm. Yeah, so one of the things that one of the effects is that because of the extreme rainfall and the surges in the levels of our rivers and creeks and streams throughout the county, a lot of our stormwater pumping plans had to be kind of put on hold and wait until we had downstream conditions that would allow us to do that. We had areas where our pump stations were completely flooded and we couldn't even get to and access them. We had others that lost power. And so, the amount of rainfall, we describe it as a 200 to 500 year event, which really is just a way to describe the probability of an event like this happening. So it's like less than 0.5% chance in a given year. Nobody in the state of Florida designs stormwater systems or infrastructure for that kind of event. So it overwhelmed even our natural rivers and the creeks and streams that flow into them. The Hillsborough River got to the highest level that had ever been recorded. And not just by a couple inches, it was a full 3.5 feet above the previous record. And it stayed at that level above the previous record for almost a week.
How is that possible? I mean, that's an incredible fact. That is crazy.
And that was happening already with Helene. Like, Helene was like, let me break some records. And then Milton was like, hold my drink. I'm going to break those records. So that's really what these storms did.
I mean, not a couple inches, you're saying. 3.5 feet.
3.5 feet above the previous record that was set during Irma.
Crazy. That was the previous record. All right, let me look at some Tomb 45 hashtags here. How do you do that? How do you do this on a computer? Damn it. What? I wish a razor would just kind of lay this down a bit. It's a nice cut, but against the grain. Against the grain. It's a nice cut though. I like the texture. I wish this would have been laid down a little bit. We're wasting so much fucking time here. You promote the event, they funnel to the website, they read what's included in VIP, they're excited about a great event, they want to sit front row at a great event. Whether it's $200 in nosebleeds or $10,000 on courtside seats, $10,000 is worth it to the people who pay for it. Whatever, nosebleed tickets is worth it for those people who pay for it. All of our VIP seats are almost sold out. We've not sold general. Let's make a great event, and that seating will be worth it. This is like raising premium prices and adding a damn foot massage to it to try to make up for your lack of confidence that it's worth it. That's your problem. That's not their problem. I'd like to focus on making a great event. So what does that look like? We have the panel. We have these educators. Is there lighting? Is there giveaways? Is there a ceremony? Is there? That's what I'd like to focus on. This is not a problem we're fixing. This is so low in the totem pole. If at the very end we want to add a clipper or some shit, I don't know. Let's do that. If we want to add a free month of something, let's do that. But I don't understand why we're trying to fix this. The data tells us this is selling. They want front seats to a great event. All right. Talking about EWP. Dre's stressed. He wants it to be the best event ever, but sometimes we focus on things. I know I do. On things that could be low priority, Man, a long time ago. It was a long time ago. Hey, long time ago. That was 2 years ago, bro. Time flies, bro. Time freaking flies. All right, let's get some work done. Listen to something in the background while we try to get some work done. Am I using OBS Live to live stream now, or the software we talked about in the mentorship? I use what's in the mentorship, so either Tela or I use Ecamm most of the time. Ecamm's my go-to. Just what's in the course. I don't like OBS. Ecamm is way better than OBS in my opinion.
Luxury realtor Josh Altman joins us now. Josh, you sell a lot of homes in LA, obviously. When we see fires like this, what happens to the real estate market after the fires?
Yeah, Stuart, I wish I was here celebrating a big sale or something like that, but unfortunately we're here talking about 1,000 new renters and buyers that have now unfortunately entered into the LA real estate market. My phone over the past 48 hours has been ringing nonstop with different types of calls. First, you have the call for immediate occupancy in a turnkey property where somebody can put their family and then figure out where they're going to go. And then you have the next call for the long-term leases for the 2 years, maybe even 3 years, because that's how long it's going to take to build these houses. And then you have the other call, which is the people who are not going to go back to places like the Palisades. It's going to take too long. You have neighborhoods that are going to be built. Are they going to want to finish their house and then sit there amongst construction for the next few years with their children in the house? It's not going to happen. So they're actually going to end up selling the dirt and actually looking to buy houses now. So to give you some sort of color of what's going on, we typically at the Altman Brothers, we list about $150 million worth of real estate a month. In the past 48 hours, we are listing $150 million worth of real estate. That's how much action we're seeing in the LA market. Now, on the other side of the coin, you have, of course, the landlords, right? They're going to put their houses on the market even if they didn't want to, and they're going to charge a premium, which is an unfortunate thing because they think that the insurance companies are going to be paying for this. And then, of course, you have people that are putting houses on their market for sale in places like Brentwood, Santa Monica, Bel Air, Beverly Hills, because it's close enough to where their regular life used to be. So that's where they're looking to purchase houses.
It seems to me you can't rebuild, certainly can't rebuild quickly until you fix all these green rules and regulations. Is there going to be a change in those regulations, a change quickly?
This is California. Nothing happens quickly, unfortunately. The average build time for a house is about 3 years. That's about a year in the permit process. You have to hope that if people lost their house to a fire, they're going to go to the front line. I don't know if that's been approved or not, so they can actually break ground immediately. But we're realistically talking about a 3-year process just to do that. We're not, and the hillside buildings, forget it. That's a whole different animal. That could be 4 years, 5 years. Malibu is notorious for taking the longest time to build. Developers just stay out of that area because it could be 7 or 8 years. The other problem is with the insurance money is the cost to build. So even in a place like the Huntington Palisades, which the entire neighborhood unfortunately has been destroyed, these are 7,500 square foot houses on average. They're going to average from about $8 million up to $25 million. You are not going to be able to recreate a house that you were living in because your build cost is going to be at least $1,000 a foot, if not more.
I guess you've got an insurance nightmare looming. It's happened already. That's not going to help, is it? How's that going to be resolved?
Well, so we have been dealing, just so we're all clear, we've been dealing with an fire insurance nightmare for well over the past couple years. When I tell you the amount of deals that have not gone through because somebody falls in love with the house and then they realize that their fire insurance is twice as much as their monthly mortgage. I can't tell you how many deals have been killed in the past. Now, I mean, is it even going to be obtainable? I don't know. I don't see that happening. And that's a whole nother problem that we have to deal with. Anywhere where you go, up in Bel Air, up in Brentwood, up in Beverly Hills, up in Malibu, very high up towards Mulholland, towards the mountains, you're going to have to bake into the price, and it is going to be reflective on the sales price of how much it's going to cost for your fire insurance. And it is going to be huge.
It is indeed. Josh Oldman, thank you very much for being with us.
I want to talk to you about a formula, better stated, a ratio that you need to absolutely know like the back of your hand if you want to grow a big ass business. And if you understand this number, you'll be able to.
All right. Speaking of that software, I need to make a video real quick. Do I still pay for this shit, man? I got so many subscriptions. I don't know about you guys. I got so many subscriptions that I pay for that I shouldn't be paying for. Come on, you know what? Let's go to Alibaba and let's see what clippers are out these days. Did I spell that wrong? There we go. Barber clippers. Let's see what the barber industry has to look forward to. We've seen these all over the place. It's crazy, bro. Fake low pros. Oh, look at these. What do you think, guys? Should we just do this? Should we just do this and slap Tomb 45 logo on these and sell them for a little bit more, like everybody else is doing, and getting celebrated? And all the barbers are buying into their marketing. The same clippers. Same clippers. Imagine there was nobody to copy. What would we get? Imagine there was nobody to copy. Which one you guys think we should do? And then look, get them for $14, sell them for $100, sell them for $50. How come these clippers are being resold for? How much are these clippers being resold for, guys? I'm curious. Oh look, Babyliss. Both of the Babyliss. Look, the Babyliss shaver that they came out with. Oh look, low pros. Should Tomb 45 do a cash grab like everybody else so that we can actually develop tools, develop innovation? Oh, these look like some tools I know. Look, we could use these. Just put 245 on it. You know, sell them for $100 like everybody else. Oh my God, they got the low pro FXs. This is a crazy industry, bro. What a crazy industry. Let's see, are there other tools? What's another industry? I was gonna say tattoos, but no. I know sneakers are heavily crazy. Yeah, when I used to use the off-brand tools, they weren't that good, but now they're a lot better. Now they're a lot better. Vector motor, 9,000 RPM in this beautiful case. I could sell 3,000 of these. Look, metal body, put the Tune 45 logo on it. Right? Get them for $50, sell them for 120. Give you a 20% discount code, a 30% discount code. Talk about how the big brands are robbing you. How long will that last? It's a cash grab. What do you guys think? Should we do it? It's crazy, bro. Now, the real question is, what would it cost? What do you need to develop a clipper from scratch? And what would it cost? Right? Let's see if ChatGPT could tell us. What equipment would be needed to manufacture in mass hair clippers? You think ChatGPT would be able to tell me? Ooh. So you got to be able to create rapid prototyping equipment. 3D printers that can do this, CAD software that can do this, rapid prototyping machines. Manufacturing equipment, you need injection molding machines for producing plastic housings, handles, and other components. CNC milling machines for precise cutting and shaping of metal parts, blades, and motors. Stamping machines, die cast machines, coil. So let's look at the pricing for each of these machines. Oof. Ooh. It's actually not that bad. But we need something that'll make big enough items. You're probably gonna need something like this. Look, this is a big machine and it makes little stuff, combs, lighters. I don't think that's even big. That's good enough to make clipper housing. Oh yeah, maybe so. Look. But you really got to go, you got to go to the factory and you got to talk to them and you got to tell them what you're looking to make. So I would say probably if you're going to buy the right machine delivered, you know, you're going to have to put this thing in a container. There goes $6,000 right there. You're gonna have to get it installed, like get a professional to put it together. Once it does reach the States. So I'm assuming you're gonna have to buy the big boy machine. Let's say 35K, 40K. I'm gonna put. There's some that are 20, but I don't think they'll be big enough. So I'm gonna go with 30. I'm gonna go with delivered to the house, fully put together. I'm gonna put $60,000. This is a Chinese machine. If you were to do something that you bought in the States, probably gonna be more like $250,000. And then let's be a little bit more conservative and let's put 70K. Okay, 10% buffer. That's more than 10%, but you guys get it. All right, so we only got clipper housing. This is gonna be for blades and motor components. We're gonna do like wall, and I think I could be wrong, but I'm pretty sure not wall, but some of the American clipper companies, even though they make all the other components, they probably import the motors. So we got a CNC machine. We have a CNC machine through FFC, through our truck manufacturing company, but I don't know if it's the right machine that would do small components. So I'm gonna say, for the right one, we're gonna go another 30, 40K. You got 28, 30,000. That probably would work. 25, 26 would probably work. But you got to get 45. Damn. But you got to get it delivered and you got to get it put together and all that stuff. So I'm gonna put another 40K for that. We're not even close to being done here. And we still don't know how to use these machines. So then you're gonna have to pay somebody to get to teach you how to do it, right? Good luck. You're gonna have to hire an engineer with a 6-figure salary to help with all of this, right? That'll know how to use these machines. So you got a stamping machine, 100 grand, boy, you tripping. I'm gonna put 20 grand for the stamping machine. 30. Let's put 20 grand, 30 grand delivered, all that stuff for the stamping machine. What else we got? Die casting machines for motor housings. Insane how this thing knows everything. Die casting machine for motor. So this is 20. So we're gonna go with 30 for that machine as well. $30,000. So let's go with motor production, coil winding machines. Jeez, I'm talking about, we're going from scratch, my boy. Hot selling cable winding machines. So they look like they're 4,500, 5 grand, 10 grand. We're gonna go delivered. Look, 10 grand. Delivered, 15,000. We're gonna go with 15 grand here. Okay. Next step is we need whatever the hell this is. And then you're gonna need experts in each of these. Look, 10 grand, 30 grand. I'm gonna go 20,000. I'm gonna go 30. I'm gonna go 20 grand on this one. 20 grand on this one. Jeez. Balancing machines. don't even know that this is the right machine that I need. But I gotta assume that regardless, maybe it's 10 grand. What is to ensure motor runs smoothly without vibration? All right, we're gonna go 15 grand on this one. All right, grinding machines. Geez, for the blade production. I don't have time for this. So we're going to go 10, 20, 30, add another 10 on top. So we're at 40 grand. 10, 20, 30. We're at 70, 80 grand, let's say. Oh my gosh, we're not done. Guys, $1 million at least, minimum. $1 million I'm going to go with by the time you get the skilled engineers and technicians, quality control specialists, assembly line workers. So you got all of this. Just you haven't even made a single thing. And by the way, what about the materials? What about the materials? You don't have the metal, you don't have the wiring, the copper, the plastic pellets. $1 million, and you haven't even developed a clipper yet. You haven't printed one clipper. That's just to get started. Now, could you start with motors or blades? What would you start with if you were going to start with one thing? Would it be blades, motors, or the body? What would you start with? Westwood, I don't have a scheduled time, bro. I just work. I just work and then I go live while I'm working. So, by the way, EWP February 16th, Tampa. I will see you guys there. But I'm glad. I'm grateful that you get value out of it. So, I'm just making stuff. I gotta make a advertisement here too. Hey, got your tickets? That's what's up. Well, no, my Instagram comments aren't popping up. Big ups, boss, changing the game in England with 6-figure course. Let's go. Fold your clothes. Let's go. That's dope. All right, I gotta do this ad real quick, so don't mind me. Let me see. How am I gonna do this? Oh, that makes it easy. No, that's fire. That's fire. I want to get to know you. I want to do some things. I got to work on the Tune 45 website, get it all cleaned up. What was I doing? DFSformula.com. All right. Why does it look like that? But yeah, I'm actually intrigued by this. It's definitely a squirrel. Look at this.
You find this design in just about all the cheap beard trimmers and a few expensive hair clippers. So there's a DC motor which converts circular motion to linear motion. In the two little diagrams you can see it doesn't matter which direction the motor rotates, the linear motion will always be the same. Personally, they are my favorite because most of them come with a rechargeable battery and they can cost as little as $10. So if you break, you don't have to fix them, you can just toss them out and get a new one. Also, some of the higher end models have variable speed switches or a turbo mode in the cheap model I bought a long time ago. Next, we have the Barber's workhorse, also known as the magnetic hair clipper. Magnetic hair clippers are the fastest in the market, and it is because as AC power comes in at 60 Hertz or 50 if you live in Europe, a sine wave creates the strongest magnetic field in the coil twice, once in the positive peak and once in the negative peak. Between the peaks of the sine wave is when the spring pushes on the arm to move the blade, which means that the blade of a magnetic hair clipper moves at 120 Hertz per second, which is 120 Hertz times 60 seconds per minute equals 7,200 RPM. Now the small drawback from this high speed and the spring push action is low torque in magnetic hair clippers, and with
This is why it drives me crazy when barbers say that magnetic clippers are the most powerful clippers. They're the fastest, but they have the worst torque. Oh, it'll go right through that. No, it won't. You know, like that's why I tell people, yeah, rotary clippers are not the fastest, but if you want more power, if you want to be able to go through bulk better, rotary has more torque.
this high speed also results in high heat of the blade due to friction. Lastly, we have the dual magnetic or pivot motor design similar to magnetic hair clippers. They use the AC power to move the blade, but instead of the spring push action, it relies on the magnetic pull. The pull force on the arm is equal thanks to diodes, as each coil see either a positive peak or a negative peak. And the blade moves once every sine wave, so we can calculate the speed as follows. 60 Hertz times 60 seconds per minute equals 3,600 RPM, which is half the speed of the magnetic hair clipper. But the pull force of clippers result in very high torque. However, the lower speed also is a benefit because the blades don't get as hot. And in conclusion, we can see all the three designs working simultaneously. They have their limitations and advantages. But my goal in this video is not to show you how one is better than the other. It's just to show you how they work and how they're different. I hope you like this video, and thank you for watching.
This is not true. 99.9% of barbers do not know this. I don't think that's true. I think a lot of barbers do know this.
If you look around your house, you will see many devices that have electric motors, such as kids' toys, table fans, toothbrushes, hair dryers, and this electric cutting knife.
Excuse me.
But how does the electric motor work? You turn it on and somehow it starts rotating. Why is that? In this video, we'll cover the basics of electricity and magnets, and then put it all together to understand how the motor works. This video is sponsored by Brilliant. Let's start with something called a circuit. You have a battery, some wires, and a device that uses electricity such as a light bulb. Electricity flows through the circuit, but as soon as there is a break in the wire, the electricity stops flowing and the light bulb goes off. The path must be complete for the circuit to work. This is best done through the use of a switch. Electricity is flowing down the wire. This is called conventional flow. If we take the battery out and flip it, then the current will flow the other way. The light bulb will still work in either case, but there are some devices that will work differently depending on which way the current flows. Okay, so that's the basics of a circuit. Now let's come over here. This is a magnet. It has a north pole and a south pole, and it likes to attract other metal objects like these paper clips. If you bring another magnet towards it, opposite poles attract, and the same poles repel. Magnets don't have to be in this shape. For example, some magnets might be more flat like this. You can think of this magnet as always on, it's always working, you can't really turn it off. That's why it's sometimes called a permanent magnet. It's made up of many smaller magnetic domains that are lined up in the same direction. But later I'll show you a type of magnet where this is not always the case. Let's take one of our permanent magnets and drill a hole in the center and put it on something that will allow it to spin. Now bring another magnet towards it. Our spinning magnet will immediately line up until opposite poles are right next to each other. Now switch out the side magnet. The same poles repel and opposite poles attract. If we keep switching out these side magnets, then our spinning magnet will just keep spinning. This concept of the spinning magnet is really important. We'll come back to it in a moment. Here's a metal bolt which is not a magnet. It's made up of magnetic domains, but they are pointing in random directions. Now let's take a wire, wrap it around several times, and then create a circuit. The current through the wires forces the magnetic domains to line up. That means we've just made a magnet, or more specifically, an electromagnet. It can do the same things that a permanent magnet can. It can pick up pieces of metal, and it has a north and a south pole which will attract or repel other magnets. But the electromagnet is special in the sense that it can be turned on or off, just like the light bulb. You can't do that with a permanent magnet. Now watch what happens when we flip the battery. The electric current was flowing this way, but now it flows the other way. This will cause the poles on our magnet to switch places. North will become south, and south will become north. This is called reversing the polarity of an electromagnet. Instead of flipping the battery, an easier way to do this is to just switch the wires. You should be aware that the electromagnet will get very hot if it's on for a while. Just a caution in case this video inspires any science projects. Let's come back to our spinning magnet. This time we'll replace the spinning magnet with our electromagnet. As soon as we connect the wires, the magnet turns on and it lines up with the side magnet. Now in reality, connecting these wires would prevent the bolt from spinning freely, but what's important here is the concept of the spinning electromagnet. Now let's switch the wires to reverse the poles on the electromagnet. The same poles repel and opposite poles attract. Now reverse the polarity again. Same poles repel and opposite poles attract. If we keep switching the polarity, our electromagnet will just keep spinning. To make this stronger, let's bring in another permanent magnet on the side. Notice how this side has the south pole towards the center, and this side has the north pole towards the center. The side magnets work together to spin the one in the middle. This right here shows the very basics of an electric motor. But we need to make a few improvements. The two side magnets can be replaced with stronger curved magnets. And instead of a bolt with wires, we're going to use a metal loop. This is called the armature. Connect our wires and we have a circuit again. This time you can think of the electromagnet as flat like this with the south pole pointing up. Now the armature will spin until opposite poles are lined up. We can keep it spinning by switching the wires just like we did before. But this is a lot of work to sit here and manually switch these wires. We need to add something to the armature called a commutator. It's a ring with gaps on the opposite sides. The commutator will spin along with the armature. Now we connect the circuit with 2 brushes on the side. These brushes will slide along as the commutator spins, and they are spring-loaded so that they always maintain contact. The current flows from the wire, through the brush, the commutator ring, the armature loop, and back through the other side. Now we have our electromagnet and the armature spins. As we come around this time, the brushes will switch contact to the other side of the commutator ring. Remember, there's 2 brushes, so this is happening on both sides. Before the switch, the current in the armature is flowing this way. After the brushes switch sides, current will flow the other way. This means the electromagnet switches polarity, which will cause the armature to keep spinning. This commutator ring does the same thing as switching the wires like we were doing before, but this time it does it all on its own. It will continue to spin as long as we're connected to a battery. Disconnect the battery, no more electromagnet, and the spinning stops. Now, so far we've only used 1 loop on the armature. This will cause our motor to have an irregular speed, and in fact, we could get stuck in this position, with the brushes halfway between commutator segments. What we can do is split the commutator ring and then add another loop. So first, the brushes are in contact with these 2 commutator segments, which turns on this electromagnet, which causes it to start spinning. Once we get to here, the brushes switch contact to the next pair of commutator segments, which means this loop turns off and the next loop turns on. Now this electromagnet wants to spin. The brushes switch contact and the next loop turns on. This keeps happening as our motor spins. It's almost like the loops will take turns being an electromagnet. Some electric motors will add many loops to the armature. This ensures that there will be a continuous spinning motion on the motor. This spinning force on the armature is called a torque. Stronger torque means a faster spin. There are some things we can do to improve the torque of the motor. Electromagnets are stronger when there are more wires. This is true when we wrap more wires around the metal bolt, and it's also true when each of our armature loops are made of many wires. The motor will have stronger electromagnets, which means it will spin faster. If you look at some pictures of real electric motors, you can see lots of wires wrapped around. And yes, this is the same reason. More wires wrapped around means stronger electromagnets. Another way to make this stronger is to use more electricity. Let's learn a few more terms here. The part that doesn't move is called the stator. In this case, it's the 2 permanent magnets on the side. These fit inside the edges of the motor case.
This is why sometimes a bigger battery does produce more power. Does make your clipper produce more power. This is why when we dropped the wall battery that we came out with, a lot of people were like, damn, my clipper's cutting more powerful.
The armature in the middle is also called a rotor. Remember, this is the part that spins. The axle goes through the middle here and then sticks out the back of the motor. What I've shown you in this video is called a DC motor. If you have a device that moves and is powered by a battery, there's a good chance there's a DC motor in it. Other types of electric motors will work a little differently than what I've shown here. No matter the type of motor, most of them will produce some type of spinning motion. Once it's spinning, we can use this to make different devices move. In this case, a kid's toy. Or even a fan that cools your room. The spinning of the motor can be converted to other types of movement, such as the side-to-side motion that we see in this fan. Or how about this electric cutting knife? Each blade is going back and forth. It all starts with the spinning of the motor to turn a gear, which then pushes these 2 pieces back and forth. So hopefully this video has made a few light bulbs go off in your brain. If you like learning new things, head on over to Brilliant. This is a problem-solving website and app that focuses specifically on math and science. The idea here is that you learn by doing. Pick a topic, it starts with the basics, but gradually it gets more complex as you go. For me, I've enjoyed how you can see these concepts visually, like the area of a circle. You get to see why the equation works. The best way to learn is to do it yourself. Master the concepts by solving fun and interactive problems. And look at that, they've even got a course on electricity and magnetism. You can learn more about the concepts you've seen in this video. Brilliant is great for anybody that is curious and...
This is the stuff people don't want to learn. And this is the stuff that makes you
The
valuable.
most advanced space telescope ever built is the James Webb Space Telescope. In this video, we'll go over how this telescope works, how it was designed and built in different places.
This guy's a badass, man.
If you look around your house, you will see many devices that have electric.
This is what I wanted to watch
This
next.
is Nikola.
So now that we got a basic understanding of what the electric motor, how that works, right? DC electric motors. Now there are motors that are brushless, and actually let's check that out, and then we'll check out this Tesla one. So let's look at how. So we saw what the brushes are for a clipper. How does a brushless motor work? All right, which one looks like a good one? This one looks good.
In this video,
Boring.
In order to make the operation more reliable, more efficient, and less noisy, the recent trend has been to use brushless DC motors. They are also lighter compared to brushed motors with the same power output.
So this is something that I remember Babeless was really, really trying to promote, but they couldn't get barbers to care. So they were pushing their brushless DC motors. Our clippers have brushless. Our clippers are brushless. They were the first to put a brushless motor in a clipper, from my understanding, and nobody cared. Nobody in the barbering industry cared because it's more expensive.
The brushes in conventional DC motors wear out over the time and may cause sparking. Thus,
Remember, these are the brushes right here. For those on Instagram, these are the brushes right here. Remember, those are the brushes. So those wear out over time, and that's why your clippers get weaker. This is why Babeless was pushing this. Everybody was like, oh, they get loud, they don't last. Technically, their motors should outlast any motor that's out there that was being used at the time, because everybody else was using DC motors. So the fact is their motors last longer, but people were acting like their motors were trash. And it wasn't that their motors were breaking. I think it was the battery that was having issues. I don't know. I could be wrong. But nonetheless, it is a fact that in regular electric motors, DC motors, these brushes wear out over time. And so DC motors do not last as long as brushless motors. Now, there could be other problems, other issues that come up with whatever solution they did to fix this. You know, when you fix something, something else might break because of it, right? So
brushed DC motor should never be used for operations that demand long life and reliability. Let's see how a brushless DC motor works. The rotor of a BLDC motor is a permanent magnet. The stator has a coil arrangement as shown. By applying DC power to the coil will energize and become an electromagnet. The operation of a BLDC is based on the simple force interaction between the permanent magnet and the electromagnet. In this condition, when the coil A is energized, the opposite poles of the rotor and stator are attracted to each other. As the rotor nears coil A, coil B is energized. As the rotor nears coil B, coil C is energized. After that, coil A is energized with the opposite polarity. This process is repeated, and the rotor continues to rotate.
So cool.
A humorous analogy to help remember it is to think of the BLDC operation like the story of the donkey and the carrot, where the donkey tries hard to reach the carrot, but the carrot keeps moving out of reach. Even though this motor works, it has one drawback. You can notice that at any instant only one coil is energized. The two dead coils greatly reduce the power output of the motor.
Yeah.
Here
so
is the
that's
trick
another,
to over.
That's another point. That's another thing. Those brushless motors, people would also look at, oh, how come why don't you guys put a bigger battery in it? Well, part of it is because these clippers don't need that big of a battery. They're brushless, so they're more efficient. They don't pull as much energy. And so, but it was hard for barbers to, I think, identify with that because they're so used to bigger battery, bigger motor, more RPM. That means better. And I'm guilty of that as well. Not understanding that there's dynamics to it, right?
Overcome this problem. When the rotor is in this position, along with the first coil, which pulls the rotor, you can energize the coil behind it in such a way that it will push the rotor. For this instant, a same polarity current is passed through the second coil. The combined effect produces more torque and power output from the motor. The combined force also makes sure that a BLDC has a beautiful constant torque nature. With this configuration, two coils need to be energized separately, but by making a small modification to the stator coil, we can simplify this process. Just connect one free end of the coils together. When the power is applied between coils A and B, let's note the current flow through the coils. It's just like the separately energized state. That's how a BLDC works. But you might have some intriguing doubts in your mind. How do I know which stator coils to energize? How do I know when to energize it so that I will get a continuous rotation from the rotor? In a BLDC, we use an electronic controller for this purpose. A sensor determines the position of the rotor, and based on this information, the controller decides which coils to energize.
Also, because of all these components, sure, you have a more efficient motor, you have one that's going to last longer, but it requires more components to make it work. And so the cost of these motors are much higher than your typical DC motor. And that's why the price of Babeless's clippers, from my understanding, were more expensive at that time, when they were trying to introduce this technology to the market. And barbers just don't get it, right? They don't appreciate this technology right now, and so they're not willing to spend the extra money. And of course, you have marketing where other brands will attack brands that are trying to innovate and bring new technology to the table and say, "Oh, they're overcharging you guys. We're going to give you a great clipper at at 30% less than what they're charging you. They're scamming barbers." That's just not, when you really go into the details, that's just not honest, right? And I'm guilty of not understanding this as well, and so that's why it's really difficult for brands to want to take risks like this, because at the end of the day, marketing wins, and if you can't get this information to the marketplace and you can't get early adoption, then you're burning money. Tomb 45 has burned money by trying to get early adoption and things that people weren't ready for, or we were trying to be first to market, and then people just kind of piggybacked what we were doing, our wave, and capitalizing on it. And they were learning from the mistakes we made, and marketing against it, right? And so because we were first to market, sure, is there advantages? Yes, but that's short term. You got to constantly improve on it if you're going to be first to market, because there's going to be people that copy your wave. And if you can't get information and the marketing done to get early adoption and get people to understand why you're doing what you're doing, then it's going to crush your business. And everybody is going to, outsiders, other brands are going to capitalize off that. Hopefully that makes sense.
Most often, a Hall effect sensor is used for this purpose.
That's the sensor.
The BLDC design we have discussed so far.
Look how the motor is so much different. It's flatter, but it's a little bit wider, so it's tricky.
Is known as the Outrunner type. In-runner BLDC design is also available in the market. We hope you had a nice introduction on the working of BLDC motors. Thank you.
That was awesome. All right, so the next one I wanted to check out was Tesla's motor, how they changed the game. I gotta find it. Here it goes. How they changed the game with electric motors. Now that we got an understanding of what DC looks like, what BLDC, brushless DC, and now we're gonna check out how Tesla reinvented the electric motor. Let's check it out.
Tesla, the greatest inventor of all time, and this is his greatest invention, the AC induction motor. In the early 21st century, modern inventors like Elon Musk started putting these AC induction.
Oh, okay. So this is just, I thought it was actually Tesla, the car, the manufacturer. Maybe I'm wrong.
Induction motors into electric cars. From this, Tesla Motors was born. Elon Musk's Tesla has been constantly improving on that century-old design, from their Model S to the Model 3 and onto their next-generation electric car that has yet to even be released. This is how Tesla reinvented the electric motor. The AC induction motor is a product that goes back to the early days of Tesla Motors and the development of their first roadster vehicle. But in the grand scheme of things, the induction motor actually tracks its origin back to the early days of the Industrial Revolution. Alternating current is the kind of electricity that surrounds us on a daily basis. It's what comes out of the sockets in your wall and moves through the power lines up and down your street. Nikola Tesla is widely considered to be the father of alternating current electricity and was a pivotal figure in adopting AC to power the US electrical grid around the turn of the 20th century. Many people consider Tesla's greatest invention to be the alternating current induction motor, essentially a device that will transform AC electricity into mechanical motion, and in turn, when used in the opposite direction, an induction motor can turn motion into electricity. One of the first large-scale applications of Tesla's AC generator was capturing hydroelectricity at Niagara Falls. When we say alternating current, we are really talking about the direction that electricity is moving through a circuit. So, for AC electricity to work, the direction of the electric current has to continuously alternate between forwards and backwards. This is a bit difficult to imagine in the context of our own electrical grid. As far as we can tell, electricity flows out of the generating station and into our house, but in reality, it's in a constant state of movement back and forth. This is a characteristic that allows AC electricity to be transmitted at high voltages over very long distances and then converted into lower voltage for final delivery to the consumer. The alternating flow happens so fast that we only perceive the electricity as constant, but in reality, the direction of electricity alternates 60 times per second in North America. So how does this apply to electric motors? Well, it's all about magnets. So when you transmit electricity through a conductive material like a copper wire, you also create a magnetic field in that wire. This is an electromagnet, and once you stop the flow of electricity, the magnetic field will also dissipate. Now, if you transfer electricity in one direction through a conductor, you create a magnetic pole, either a south pole or a north pole. And then if you were to reverse the flow of electricity through that same conductor, you would also reverse the polarity of the magnetic field, so as the direction of electricity alternates, so does the north and south pole of the electromagnet. There are two essential components of an electric motor, the stator and the rotor. The rotor rotates and the stator remains stationary. Easy way to remember which is which. Now, as the name suggests, an induction motor uses a rotating magnetic field in the stator to induce a rotational force in the rotor. Here is how that breaks down. Your stator is essentially a ring of copper wire that is arranged into coils that run from the front to the back of the motor. Each coil of wire is wrapped around a piece of iron, so when electricity is flowed through the coil of wire, it becomes a powerful electromagnet. The polarity of each magnet is determined by the direction of current. So by alternating the directions of the electrical charge being applied to each subsequent winding and flipping each polarity in sequence, we create a rotating magnetic field that travels around the ring of the stator. The speed at which the magnetic field rotates can then be controlled by the rate at which you can alternate the flow of electricity. The rotor in this case is a much more simple component. There are various different kinds of rotors used in different induction motor designs, but the one that we are going to focus on is different kinds of rotors used in different
Squirrel cage rotor, wound rotor, magnet rotor. Crazy.
Induction motor designs, but the one that we are going to focus on today is known as the squirrel cage rotor. It gets the name because the structure is a cylinder made from aluminum bars that run from the front to the back of the rotor with circular metal end caps. There is no supply of electricity flowing into the rotor, and it contains no natural magnets. It's literally just a metal cage that can freely rotate, and yet the rotor can be transformed into a magnet by the rotating magnetic field of the stator. One of the interesting things about magnets is that they move relative to a conductive material. They can induce an electrical current into that conductor, which in turn creates an electromagnet with no contact required, just relative motion. You can see this by dropping a magnet straight down a copper pipe. As the magnet falls, it will induce a magnetic field into the pipe, which will then work against the magnet itself and slow the fall of the magnet through the tube. So the further it falls, the slower it will move through the air due to resistance from the induced magnetic field in the copper pipe. The same thing is happening inside the induction motor. By rotating the magnetic field around the stator using alternating current and electromagnets, a magnetic field will be induced in the bars of the squirrel cage rotor. That induced magnetic field will react against the magnetism of the stator. We know that magnets with the same polarity will push against each other, and this force of magnetism will cause the rotor to turn in the direction of the stator's magnetic field. So the faster you alternate the flow of current through the stator, the faster the rotation of the magnetic field, and the faster the movement of the rotor due to the magnetic push effect. The only caveat we need to remember is that the rotor will have to move at a slower rate than the rotating field of the stator, because the magnetic field is created by relative motion. If the two are turning in sync, then there's no longer any of that motion in play. The rotor will demagnetize and slow down. From the time this induction motor was first patented by Nikola Tesla, 1888, to the present day, AC motors have been a staple of industrial society. We see them in everything from elevators and streetcars to ceiling fans and washing machines. Anything that plugs into the electrical grid and spins is more than likely to have an AC induction motor inside. So when it came time for Elon Musk and his crew of founders at Tesla Motors to choose a power source for their first electric roadster vehicle, there was one very obvious candidate, the AC induction motor. And when used in an electric vehicle, the design gives you one significant advantage. We know that when you rotate the magnets of the stator faster than the rotor, you electrify the rotor and create a magnet. But when you spin the rotor faster than the stator using an external force like a wheel, you electrify the stator, which can then transfer the excess energy back to the battery pack and increase the driving range of your vehicle. This is how regenerative braking works. Tesla retained the AC induction motor as their primary drive unit into the Model S and X. This allowed the relatively large and heavy vehicles to achieve mind-boggling feats of acceleration from a standing start, but they also came with a significant drawback that needed to be solved. So the beauty of the AC induction motor is its simplicity. Coils of copper wire, some chunks of steel and iron, a squirrel cage of aluminum bars, not much to it. And that's exactly why the motors in appliances like air conditioners and washing machines can run for decades without failure. The downsides of the original induction motor start to show themselves only when you go in search of maximum power and efficiency, which is exactly what Tesla was looking for when they designed their Model 3. Okay, so everything that we just talked about still applies to this new motor that Tesla created for their Model 3, but with one key addition: permanent magnets. Specifically, they added permanent magnets to the rotor, so now instead of an aluminum squirrel cage...
Yo, imagine if you use a motor like this and you can create regenerative charging to that motor or to that battery in your clipper with the lever pull or something, right? Every time you move the lever, it's regenerative. That'd be insane. No barber would pay for that. It would add $20 to the cost, and now clipper is $20 more. Or would they? Just depends on the marketing.
We have this dense iron core filled with strips of a magnetic rare earth element called neodymium. The technical name for this new motor type is IPM Syn RM. That means internal permanent magnet synchronous reluctance motor. It's complicated. Here's the scoop. You could make a permanent magnet motor by taking a metal cylinder, sticking 4 magnets to the outside with south poles on the top and bottom, and north poles on the sides. That would be your rotor. And then when you stick that inside the stator that we talked about before and start rotating the electromagnetic field in the stator coils, your permanent magnet rotor will follow. Now, we can actually spin the rotor at the exact same speed as the rotating magnetic field of the stator, because we are no longer relying on relative motion to induce the magnetism in the rotor. This already gives us higher efficiency and more power, particularly when accelerating from a stop, because we have these two very powerful magnetic fields that can instantly push off from each other. But there's a big problem. 2 problems, really. For one, permanent magnets stuck to the outside of the rotor will have a tendency to come unstuck due to centrifugal force, so the faster the rotor spins, the more likely it is to fly apart. But even more importantly, reason 2, is that the rotation of the permanent magnets will start to induce their own magnetic field into the stator coils at high speed, and this is going to be opposite to the electromagnetic flow in the stator, and that force is going to want to slow down the whole system. This is called back EMF, and the faster the rotor speed, the more back EMF you get. To combat these 2 downsides, we introduced the design of a reluctance motor. So aluminum and copper are only magnetic when you flow electricity through them, but iron is naturally attracted to magnetic fields. So that means we can use it as a rotor material inside our same old electromagnet stator, and that iron rotor will follow in sync with the rotation of the stator's magnetic field. Again, there is one caveat. We need to cut channels into the iron material that line up with the shape of the magnetic field that surrounds it. This will align the magnetic reluctance of the iron core with the magnetic field of the stator and allow them to rotate in sync. This is our synchronous reluctance motor. It's a very efficient motor design, and it works very well at high speed because there is no back EMF created by the iron rotor. The downside here is that a reluctance motor has very low power density when accelerating at low speed because the rotor can only follow the rotating magnetic field of the stator. You don't get that instant push effect of 2 magnetic fields working against each other. Now all we need to do is add magnets to the rotor and we get our perfect combination. Those channels that we cut into the iron core make the ideal location for our permanent magnets to live. This is our internal permanent magnet. By placing them inside the iron rotor, we reduce the permanent magnet's effect on the stator windings.
That's genius. And now the magnets won't fly out.
And thereby reduce the problem of back EMF. Now, there is still a very complex task here that involves balancing the reluctance effect of the iron core with the magnetic push of the permanent magnets. You see, you want to utilize the power of permanent magnets during acceleration, but then cancel them out and switch over the efficiency of reluctance at cruising speed. This is all handled by very advanced software controlling the magnetic field of the stator that we cannot even begin to explain. And this is why the IPM Syn RM motor was never widely used until Tesla came along. And now Tesla is about to take this design to the next level. With the motor design for the Model 3, Tesla was able to maximize both power and efficiency, but it did come at a cost. If we remember back to the original induction motor, it came with a relatively simple and cheap rotor made of aluminum bars. By switching to IPM Syn RM, Tesla introduced the rare earth element neodymium into their rotor, so the cost in this instance is money. It's a much more expensive motor. Now Tesla is dedicating their research and development into a next-generation vehicle platform that is supposed to dramatically reduce cost while maximizing efficiency. This will serve as the base for their upcoming robotaxi vehicle. From what we learned last year at Tesla's Investor Day, the designers are achieving much of that cost reduction by eliminating rare earth elements from the motor's composition. Now, it's not that neodymium is particularly scarce in the overall composition of the Earth, but it is difficult to locate near the surface, and you typically won't find large concentrations all in one place, so therefore the cost is relatively high, and the supply is relatively low. But engineers still prefer neodymium for electric motors because it has a strong magnetic field that won't degrade over long periods of use, so it does justify the cost. Now, Tesla is saying that they can get by without the need for any rare earth elements in their new magnets, so what will they use instead? A widely popular material for making magnets is called ferrite. This is a ceramic material of mostly iron oxide, also known as rust, combined with additional metals like manganese, nickel, and zinc, but it doesn't particularly matter which one. You'd find ceramic ferrite magnets in everything from speakers to electric guitars and cordless drills. They also help keep your refrigerator door closed, so it's a very common and affordable material. The downside of ferrite compared to neodymium is magnetic strength. You would need a much larger quantity of ferrite to match the strength of a neodymium magnet, and there's not much extra space to go around inside an electric motor. We know that Tesla can make some of this back by increasing efficiency. They've done that in the past. Just in the time between Model 3 and Model Y, the engineers were able to reduce the amount of rare earth material required for the electric motor without sacrificing any power. But inevitably, by switching over to a ferrite magnet, Tesla will lose some performance in their next-gen vehicle. So now, instead of going 0 to 60 in 6 seconds, it might take 8 or 9 seconds.
Ain't a damn Tesla out there that does it in 6. They do it like in 4, 3, some of them do it in 2, in 1.9.
Is that the end of the world? Absolutely not. This is a vehicle made for mass transportation.
So if it does it in 5 or 6 as opposed to 2 or 4, but the cost is substantially lower with some marketing.
Not the racetrack. Going all the way back to Nikola Tesla, good inventors are simply trying to extract more functionality from the world around them. How can we do more work with less energy? How do we combine different principles to create something new and more effective? And that is what Tesla, the company, has continued to do throughout the past 2 decades. This is Nikola Tesla.
All right, so we've been building a clipper for a while now. With how much money you would need minimum to build an entire clipper from scratch. Not even to build an entire from scratch, just to have the equipment to build an entire clipper from scratch. I would say another $1 million, $2 million, $3-4 million minimum. Like, and this is hacking it. But we also went into how the motors work and what all goes into it, and are there ways to improve a motor? I don't know. I don't know that you need more than what's out there, and that technology, I feel like technology is already amazing. But I am interested to know what's going on with that vector motor and that everybody's talking about, which is a little bit different, these magnetic motors, right? As opposed to these rotary clippers. What makes those motors so good? And barbers are liking them. I like rotary, but people are really liking this other motor. So I want to do a deep dive on that here soon. But these are rotary motors, how they work, and measuring up, which ones are the best. So we covered a lot. So we covered putting together pretty much a manufacturing factory for clippers. We covered the differences between different types of clippers, right? You have magnetic, pivot, rotary. And then we went into a deep dive on actual rotary motors. And that was a lot of fun. So I think the next one, we'll go into these new vector magnetic motors, do a deeper dive into those motors, and see if there's efficiencies that can be made in there, and what kind of technologies are coming out that are making those better. So if you guys are liking this series, let me know.